This is the screencast for section 8.2, example 8. Now we're going to work with the indeterminate forms 1 to the infinity, 0 to the 0, and infinity to the 0. First, we're going to look at 1 to the infinity. Now, a little blurb up here says, limits that lead to the indeterminate form 1 to the infinity, 0 to the 0, and infinity to the 0 can sometimes be handled by taking the logarithms first. So with these three, the exponent types, why not take the logs? It helps you handle those exponents. Then we use L'Hopital's rule to find the limit of logarithm and exponentiate to reveal the original function's behavior. Now the reason that works, if you look over here, it says the limit as x approaches a of the natural log of our function equals L, and L would be some sort of limit, 5, 10, 1/4, whatever it is. That would imply that the limit as x approaches a of our regular function equals, now here, the limit as x approaches a of e to the natural log of our function. So these two statements mean the same thing. I've just created a log base e of f of x and then made that the exponent of base e. So e to the log base e of f of x would simplify to be f of x. So those are the same. And then therefore that would equal e to the L, because the limit as x approaches a of the natural log of f of x equaled L. So we would have that limit in the exponent as L. And a, what x is approaching, can be infinite or finite. It doesn't matter. So let's look at example 8 and see what this all looks like. We're going to work with the indeterminate form 1 to the infinity here in example 8. So we're going to find the limit as x approaches infinity of 1 plus 1 over x to the x. Well, if I plug in or think about what happens as x approaches infinity, I have 1 to the infinity. 1 plus 1 over infinity. 1 over infinity, 1 over a really large number is 0. So 1 plus 0 to the infinity, 1 to the infinity. Well, since this indeterminate form is exponential of sorts, I could use logs. So that's what I'm going to do. I'm going to take our original function and call it f of x. Then I'm going to take the natural log of both sides, log base e. Well, the x becomes a coefficient. The exponent in the log becomes a coefficient from one of your log properties. And now I want to create a situation where L'Hopital's rule comes into play. So I want to change this x as a coefficient to a denominator, the natural log of 1 plus 1 over x, now all over 1 over x. So instead of multiplying by x, I'm dividing by the reciprocal. Which means that I can make the conclusion the limit as x approaches infinity of the left side will equal the limit as x approaches infinity of the right side. So now that I'm taking the limit, let's think about what happens as x approaches infinity. Well, the numerator, the natural log of 1 plus 1 over infinity. So 1 over infinity would be 0. The natural log of 1 is 0. And then 1 over infinity again is 0. So we have a 0 over 0 situation, which we're very familiar with now with L'Hopital's rule. So I'm going to proceed to use L'Hopital's and take the derivative of the numerator, followed by the derivative of the denominator. Oh, look, how nice, those cancel. And then after I simplify a little bit, as x approaches infinity, I get 1 over 1 plus 0, so that would actually equal 1. Now this isn't my answer. 1 is not my answer. My answer comes from this statement up here. So therefore, the limit as x approaches infinity of 1 plus 1 over x to the x, what I'm trying to find, which is really the limit as x approaches infinity of what we called f of x, can be rewritten as limit as x approaches infinity of e to the log base e of f of x, that second statement in here. And then I already know the natural log of f of x, the limit as it approaches infinity, and that is 1. So my answer is e to the first, or e. So we did what this instruction told us to do. Limits that lead to these indeterminate forms can sometimes be handled by taking logarithms first. So that's what we did. We took the logarithms, so to help us with that exponential situation. Then we used L'Hopital's rule to find the limit of the logarithm. That's what we did. We found the limit of the log. Then exponentiate, so that was what was done in here, e to the natural log of f of x, to find the original function's behavior. Then I'll try problem number 21. Says identify the indeterminate form and evaluate the limit using L'Hopital's rule. Alright, so the limit as x approaches 0 of e to the x plus x to the 1 over x. Well, e to the 0 is 1 plus 0 is 0, so 1. And then 1 over 0, remember as x is approaching 0, we're going to get 1 and divide by teeny tiny numbers, so that's going to approach infinity. So I have 1 to the infinity. Alright, so that's my indeterminate form. Now that's an exponential situation that tells me using logs is a good idea. So I'm going to do all of that in one step. I'm going to take the limit as x approaches 0 now of the natural log of f of x and set that equal to the limit as x approaches 0 of the natural log of the actual function. So I did both. I took the logs and the limits at the same time. That's okay. Alright, so now let's look algebraically at this and see if we can make it into a form that will help us with L'Hopital's. I'm going to take the 1 over x and make that a coefficient, which is nice because that drops the x down to the denominator. This would be 1 over x times the natural log, so the x goes into the denominator. Now it looks like I might have a 0 over 0. As x approaches 0, e to the 0 is 1 plus 0 is 0, and then so 1 total in this binomial. Natural log of 1 is 0 over 0. So I do have 0 over 0 for L'Hopital's rule. So I'm going to take the derivative of the numerator over the derivative of the denominator, simplify, and now see if I can plug in x equals 0. E to the 0 is 1 plus 1 is 2 over e to the 0 is 1 plus 0. So I get 2 over 1, which is 2. Now that's not my answer. That's the limit as x approaches 0 of the natural log of our function. I want just the limit as x approaches 0 of our function. So this answer tells us that the limit as x approaches 0 of f of x, what we started out with, can be rewritten as the limit as x approaches 0 of e to the natural log of f of x, so exponentiating with a base of e. And then I found that exponent. That exponent is 2. So now the limit as x approaches 0 of e to the 2 is just e to the 2. It's e squared.